Okay, so I think we have all the committee members. So let me describe how the thesis defense work. I have to, I think everybody knows. But anyhow, so Akari will present roughly 45 to 50 minutes, and then we'll open it up to questions. If you have clarifying questions, you could ask even during the talk. But make sure to ask some hard questions at the end of the talk. And then we'll excuse you. Then the committee will start asking questions from Akari.
Sounds good. Okay. Should I start? Okay. Okay. Let me check. Okay, I got it. Yeah, thank you so much for coming today. I have some pastries from CO if you want to have some quick lunch. Yeah, thank you so much for coming today to attend my thesis defense. And today I'm excited to talk about my PhD work and augmenting language models. Oops, sorry. Okay, yeah. Today I'm excited to talk about my PhD work and augmenting language models to go beyond their built-in capabilities. Large language models like ChatGPT have become an integral part of society, impacting everyone's life. What makes those models truly remarkable is the ability to perform a wide range of tasks from generating image to code by following users' natural language instructions. But what are language models? Large language models are essentially neural networks with a massive number of trainable parameters trained on vast amount of text data gathered from the web. The recent progress has been driven by scaling, both in terms of data and model size. Researchers have gathered billions of pages from diverse sources on the web to capture a broad spectrum of world knowledge. Simultaneously, model sizes have grown exponentially. For instance, the original GPT only had 100 million parameters, whereas GPT-2 and GPT-3 scaled up by multiple orders of magnitude. This combination of data and model scaling has led to the success of monolithic language models, a single giant language model that captures a broad spectrum of world knowledge task capabilities entirely within their parameters. But are those models fully capable of assisting with critical tasks like scientific research? Here's an example. I wanted to see if language model could help me to stay up to date with new research papers. So I asked ChatGPT, are there any studies showing whether language models can help scientists synthesize scientific literature? ChatGPT generated several paper titles. At first glance, as you can see, all of the titles looked plausible. However, after searching on semantic scholars, I discovered that none of the papers exist. Such factual inaccuracy in language model output has become an increasingly serious problem across many aspects of society. Moreover, I asked, has anyone tried GPT-4o in this area? A model released by OpenAI in May 2024, a year ago, and the default for ChatGPT. Surprisingly, ChatGPT itself responded that no widely recognized models called GPT-4o exist. This highlights how quickly language models become outdated. Remember, training those models also requires massive investment. OpenAI CEO Sam Altman stated that training GPT-4 cost over $100 million US. This is due to the enormous GPU powers needed to accommodate this growing data and model size during training time. I hope now we're on the same page that monolithic giant language models still face many challenges, from incorrect output to inefficiency. How can we design the next generation of more reliable and efficient language models we can fully depend on? I believe we need a transformative shift from scaling monolithic models solely depending on their parameters to developing augmented language models, collaborating with external modules to extend their capabilities. Augmented language models represent a new paradigm in AI, focusing on designing, training, and deploying language models in conjunction with complementary modules. Over the past 5 years, I did pioneering research on retrieval-augmented language models, one of the most important types of augmented language models. Those models augment language models with large-scale text data, which we call data store. I will define it more precisely in part 1, but the core idea is to use a retrieval system to identify a small set of documents from this data store to improve language models predictions. This area has now become a key and rapidly growing field in both academia and industry, with major players like OpenAI, Google, Microsoft all actively involved. Today, I'll present my work, which has transformed the field of retrieval-augmented language models by addressing 3 fundamental questions. Why do we need to augment language models instead of merely scaling monolithic ones? How do we develop the foundations? And what can we achieve with such state-of-the-art models to make real-world impact? My extensive studies and real-world evaluations have shown their effectiveness across many domains and significantly contributed to their widespread adoptions nowadays. In the first part, I will present my work on investigating the limitation of simply scaling up conventional language models and show how retrieval-augmented language models can address those challenges. In 2022, the common belief in the community was that scaling alone would eventually resolve many issues in language models. However, my research demonstrated that many of those challenges stem from monolithic natures of language models and cannot be resolved by simple scaling. I was among the first to integrate retrieval with powerful language models like GPT-3 and now widely adopted approach. I have shown that they are more effective and efficient path forward, leading to rapid adoptions and progress of retrieval-augmented language models. So how can we design retrieval-augmented language models to fully unlock their potential? In the second part of this talk, I will present my work on redefining the foundations of retrieval-augmented language models to push their capabilities. Retrieval-augmented language models consist of 3 key components: a data store, a retrieval system, and language model. Existing approaches often simply combine off-the-shelf language models and retrieval system with small general domain data store. However, my research demonstrated that each component can be significantly enhanced. In this section, I highlight my contribution to language models, focusing on self-reg, which trains language models to decide when to use retrieval and self-evaluate outputs using special tokens. This approach enhances the quality of language model generation, outperforms much larger language models while balancing efficiency and performance. I will also briefly discuss key ideas from my work to improve retrieval components, creating the largest open data store, and developing new retrieval system that flexibly adapts to users' instructions. I'm excited that my work has had a significant impact on the community, opening up new research directions and shaping today's state-of-the-art models. Many of my contributions have been integrated into widely used libraries like Hugging Face Transformers, LangChain, Llama Index, which form the backbone of today's NLP and language model-based systems. Beyond the academia, my research has been directly applied in industry, influencing both startups and major tech companies. Finally, I'll show how those foundations together can lead to high-impact real-world applications. I highlight the OpenScholar project, which develops a fully open retrieval-augmented language models for scientific literature synthesis. Leading a year-long large-scale collaborations with 27 researchers, I built a new data store, enhanced retrieval generation algorithm, conducted expert evaluations, and launched a public demo. The resulting OpenScholar system, built entirely with open components, outperformed GPT-4o and Ph.D. level expert in our evaluation. Our free public demo has been used by over 30,000 researchers and practitioners across many scientific disciplines, showing its broader impact and utility. Now, let me start by answering the first question: why augment language models instead of just scaling them up? In this section, among many of language model limitations, I'll focus on one of the biggest issues: hallucination, factual inaccuracy in language model output. In July 2022, I was testing GPT-3 and was impressed by its ability to handle a variety of my queries. For instance, when I asked, "Who is Sam Altman?" it generated an accurate description stating that he's the CEO of OpenAI. Then I asked GPT-C, "Who is Akari Asai?" It confidently replied that I am a Japanese voice actress best known for starring in popular anime series. Amusing, but this is entirely fictional. Well, this example may be funny. Such hallucinations can have serious real-world consequences. In 2022, we didn't fully understand why or when language models hallucinate, and this lack of understanding led some users to blindly trust their responses with unfortunate result. To understand why this happens, let me briefly explain how language models are currently trained. The training involves two major components: massive pre-training data and language model itself. During pre-training, documents like ChatGPT is developed by OpenAI are sampled, and the language model is given the prefix ChatGPT is developed by. The model predicts the next token, and we update the model parameter so that language model learns to maximize the likelihood of the correct token, in this case, OpenAI. This process enables language models to encapsulate extensive world knowledge, language understanding, and generation capabilities in their parameters. My hypothesis was that documents discussing well-known figures, such as Sam Altman, are commonly found in the pre-training data, frequently encountered by models during training time. Conversely, topics that are less popular, such as myself, may not appear as frequently, posing challenges for those models to effectively memorize and retrieve such information from model parameters. To formalize this observation, we introduce a new concept, popularity of knowledge. This metric estimates the frequency of discussion of the concept on the web using data such as Wikipedia's page view for the subject entities. We then constructed a large-scale diagnostic dataset, including numerous question and answer pairs, spanning a broad spectrum of concept popularity. Based on this, we conducted one of the earliest studies on language model hallucinations back in 2022. Here, the x-axis represents the model size, and the y-axis shows the model performance on this new PopQA dataset. I divided the dataset into two groups: popular question, indicated as red circle, and less popular or rare questions as blue circles based on the popularity. We evaluated diverse sizes of OPT models, open language model from Meta, starting from 1 billion parameters. As we scale model size, we see performance improvement on popular questions, but the performance on rare questions, the blue circles, remains low, even when the model size is scaled up by 20 times. Eventually, GPT-3 175B, likely trained on more data than the OPT model, shows less than 2% improvement on less popular knowledge, while achieving over 30% improvement on popular questions. We concluded that scaling alone cannot resolve hallucination in long-tail knowledge, which is underrepresented in pre-training time. This is a significant issue, as such long-tail knowledge is vital for many expert domain tasks like scientific applications. Then how can we overcome such long-tail hallucinations? The challenge is that for less popular concepts, even if they appear in pre-training time, language model cannot effectively memorize them in their parameters. Then what if we could directly search the entire text data, locate a few documents about rare entities like Akari Asai, and reason over them to update the answer? This is essentially the core intuition behind retrieval-augmented language models. This enables language models to dynamically incorporate knowledge at inference time, removing the necessity of memorizing everything in model parameters. Now, let me provide a more concrete description of how retrieval-augmented language models work. Those models enhance language models like OPT or GPT-C by incorporating a data store, a collection of documents. The length of those documents depends on the model, but each typically contains a few hundred words. A retrieval model takes an input query and searches the entire data store to identify the most related documents. Specifically, given the user input X, we use this retrieval system to compute the similarity between the query X and documents in the data store to identify the top K documents T with the highest similarity scores. Then we incorporate the retrievable documents T to enhance the prediction of language models. Note that there are many different ways to incorporate retrievable documents T. In this work, we focused on in-context retrieval-augmented generation or just retrieval-augmented generation for simplicity. This approach involves appending retrievable documents T to the original input, such as a question, and then feeding them together into a language model. While retrieval-augmented methods have been studied for years, earlier research often fine-tuned language models for specific downstream tasks. In contrast, we use off-the-shelf powerful language models like open models or GPT-C without fine-tuning, which is now often commonly referred to as RAG. To my knowledge, this is one of the earliest work to propose RAG with off-the-shelf language models and quantify its impact. Now, let's see the performance across questions of different levels of popularity. The x-axis here now represents question popularity, and the y-axis shows the model performance, with the left side focusing on less popular questions. I'll show the performance of GPT-C and GPT-3 with retrieval. As shown, retrieval-augmented GPT-C, the green line, outperforms non-retrieval-augmented baseline, the red line, and long-tail questions, confirming our hypothesis that retrieval-augmented language models are particularly effective in handling long-tail questions. As a result, we found that across different model classes and sizes, retrieval-augmented language models consistently outperform their base models by large margin, simply by integrating retrieval with off-the-shelf language models. However, we also discovered there are several limitations in such simple combinations. As you can see, on the most popular questions, GPT-C already outperformed retrieval-augmented models. Why does this happen? By careful analysis, we identified several core limitations. First, GPT-C already memorized common knowledge and often performs well on frequent questions, such as knowing who Sam Altman is. Retrieval systems are not always perfect. They sometimes fetch the wrong information. For instance, instead of retrieving documents about Sam Altman, they might return results about Sam Adams. Since language models already have knowledge, we might expect the performance to stay the same even when retrieval fails. However, we found that language models can be easily misled by unhelpful context, even when they originally knew the right answer. In part 2, I will discuss how we can improve language model, retrieval models, and the integrations to make those systems more robust and useful. This work was the first to quantify language model hallucination and propose RAG with off-the-shelf language models, providing key insight into their effectiveness and limitations. Recognized as one of the most cited ACL 2023 papers, it saves the research in this area, advancing both our understanding and model development. PopQA is now widely used and integrated into multiple benchmarks and used as one of the core benchmarks for state-of-the-art language models, such as Tutor3. In summary, prior efforts have focused on scaling language models by increasing models' size or data. Yet this approach still faces many challenges like hallucinations. I demonstrated that retrieval-augmented language model can significantly mitigate such issues by precisely locating necessary knowledge from large-scale text data and incorporating them at the inference time. This also provides benefit other than reduced hallucination. In the interest of time, I won't go into the detail, but my research also demonstrates the ability to update knowledge efficiently without expensive retraining, and to substantially reduce pre-training cost by eliminating the need to encode all the knowledge in model parameters. I also led the first tutorial on retrieval-augmented language models at ACL, which has been now widely adopted in many university courses and other tutorials. Our earlier studies have inspired numerous follow-up work and industry adoption of retrieval-augmented language model, shaping today's widely adopted applications like ChatGPT search. However, as I discussed, current simple RAG systems still have many key limitations, causing real-world problems on those applications. So how can we make those models more reliable and widely useful? This is what exactly I want to answer in part 2. Let me recap the common RAG pipeline and the challenges. They consist of 3 key components: a data store, like English Wikipedia, a retrieval system, and a language model. The retriever is typically trained on QA or information retrieval datasets, although many now use off-the-shelf language models. This pipeline follows a 3 separated 2-stage processes. First, retrieving everything upfront, and then generating a response. This approach has shown to be quite effective for simple tasks like question answering. But what happened when we deal with much more complex scenarios, such as building systems like OpenScholar, where we needed to search up-to-date scientific literature, reason over multiple documents from many different papers, and generate well-structured responses? First, it would struggle with a small general domain data store. For instance, Wikipedia wouldn't provide useful documents for this type of input. Second, retrieval models trained on specific downstream retrieval tasks often fail to generalize to new retrieval setup. For instance, a system optimized for a Wikipedia-based question answering may struggle to identify the most related scientific papers to provide useful response to this research-related question. But more importantly, this inflexible 2-stage pipeline, where retrieval and generation are fully separated, paired with off-the-shelf language models, comes with significant limitations. As we discussed in part 1, even state-of-the-art models like GPT-3 often fail to distinguish between helpful and unhelpful documents, leading to prediction errors. Moreover, a fixed 2-stage pipelines can't handle different levels of information needs. Complex query like this example often requires multiple retrieval steps and during generation to ensure completeness and accuracy. For instance, in this case, we may need to include models beyond GPT-4o, which requires retrieving additional documents. Conversely, in applications like ChatGPT, many user input, such as fixing typos, don't require wild knowledge. In this case, retrieval should be skipped entirely to reduce unnecessary cost and potential errors. In summary, challenges exist across all the stages of the pipeline: data store, retriever, language models, and their integrations. How can we address those challenges to create a system capable of reliably handling complex tasks and develop advanced systems like OpenScholar? This calls for a fundamental thinking of how language models and retrieval systems are designed and trained, moving beyond simple combinations. First, I will introduce an approach to developing language models that more effectively and efficiently use retrieval. Our goal is to move beyond fixed pipelines and build a more dynamic system, where the generator selectively integrates retrieval, minimizes error propagation, and ensures well-supported outputs. Imagine the critic language model that oversees both the generator and retriever. This model determines if retrieval is necessary, and if not, the generator acts like a standard language model. When retrieval is needed, then critic prompts the retrieval system. Subsequently, the critic selects the most related documents from this retrieved result, and then feeds them to the generator model. Finally, it evaluates whether the output of the generator model is well supported by citation or not. This approach enhances reliability and control, addressing many of the limitations I just discussed. However, running multiple models in sequence can introduce additional computational overhead. What if we could teach the generator language model learn to perform this critic functionality to adaptively retrieve and self-evaluate by themselves? That's exactly what Self-Rag does. It independently handles planning, generation, and self-evaluation in a single model. Specifically, Self-Rag trains new language models with new special tokens, which we call reflection tokens. Self-Rag effectively incorporates those special tokens during inference time to guide its decision-making. For example, given an input, the model first generates a token indicating if retrieval is necessary or not. Those tokens also facilitate other self-reflection stages. This work was the first to explicitly train language models for adaptive retrieval using special tokens, a technique now widely adopted in many industry applications, including ChatGPT search and deep research. Now I'll show how self-RAG inference works with an example, and then how to train self-RAG. If the task is complex and requires retrieval, such as suggest papers showing language models' effectiveness for scientific research understanding, self-RAG first generates the retrieval token to trigger the retrieval system. Then the retrieval system identifies a small set of documents. Self-RAG generates continuation based on each document in parallel. The model first explicitly evaluates the relevance of each document to the question. In response to the question, the first document about language model for industry chatbot is unhelpful, while the bottom two provide useful information. If the response is based on unhelpful document, the generation is likely to be incorrect or at least not supported by citation. So we discard this continuation. Given the related documents, the model first generates responses conditioned on each document in parallel. And then it evaluates if the generated response is fully supported by citation or not. In this case, the second generation is just partially supported, as the corresponding documents only mention idea generation with language models. Now we have two generations in parallel. Which one should be chosen as a continuation for the next sentence? What we did in self-RAG is we take the token probability score of those special tokens and use them to rank the continuation. Specifically, we computed the weighted sum of token probability and then select the best continuation with the highest score. We repeat this process for each sentence until model completes its generation. Well, I've simplified this by choosing only the best continuation. Our default approach uses sentence-level beam search, keeping the top n generation at each sentence. Now, important question is, how can we train a language model to generate both special tokens and standard output? Since fine-grained training data for self-RAG doesn't naturally exist, we take a three-stage training approach. We first train a critic language model, which can teach the generated language model to generate reflection tokens. Then we use this critic language model to generate training data for the generated language model. Lastly, we train the final self-RAG model on the generated training data so that language model can internalize both critic and generation functionality. The critic language model is an in-house language model learned to generate reflection tokens for all fine-grained aspects for the self-RAG inference. For instance, it can evaluate if retrieval is needed or not, or if a given passage is related or not. We generate high-quality synthetic training data using GPT-4 to overcome data scarcity. Then we use this critic language model and retrieval system to transform existing instruction training dataset. Specifically, we sample training instances from existing standard input-output data, such as Stanford Alpaca dataset. We then run critic language model on each instance to generate reflection tokens. For example, as the first instance would benefit from retrieval, the critic language model would predict a retrieval token. We then perform retrieval system and evaluate the relevance of retrieval documents. Now we have predicted special tokens along with retrieval documents. We use them to define the original output to make sure it aligns with the expected self-RAG output at the inference time. We repeat this process for every instance and each sentence to construct a new training dataset, Dzen. Now we can train language models on this data. First, we add special tokens to the model vocabulary, and then we train language models on this input-output data sampled from the new training dataset. Specifically, we update the model parameter filter to maximize the log probability of the correct continuation Y and reflection tokens O, given the original input X and also retrieval document state. This is basically a standard maximal likelihood objective of language model with transformed input and output. Now let's discuss the result. We trained Serfag on top of Llama 2 7B and 13B model from Meta and compare it with off-the-shelf Llama 2 ChatGPT with and without standard RAG implementations. For simplicity, we'll focus on 13B language models and ChatGPT in this presentation. We holistically evaluated Serfag on diverse 6 datasets, highlighting 3 key ones here. PopQA, a short home QA dataset, which I just discussed in part 1. Pub-Health-Analysis QA, a multiple choice and long homogenization dataset that require reasoning over multiple documents and thus more complex than the PopQA. Model performance was evaluated using standard metric like accuracy and citation accuracy. The citation accuracy evaluates if the model output is fully supported by accompanied citation node. More details of our evaluations are in a paper. On PopQA, a simple QA dataset, standard RAG performs well and gives significant improvement as seen in part 1. However, on Pub-Health-Analysis QA, standard RAG system gives only marginal improvement. This highlights the difficulty in effectively incorporating documents in more complex scenarios. Moreover, especially open Llama models struggle to generate outputs with citation, resulting in low citation accuracy. Serfag outperformed all open language models by large margins across benchmarks and matched or even outperformed ChatGPT of most of the dataset. It also shows massive improvement from the base Llama 2 in terms of citation accuracy, suppressing ChatGPT. This demonstrates its ability to generate higher quality and well-supported responses. Serfag sparked a lot of follow-up work establishing new direction in advanced retrieval-augmented generation and language model training with Retrieval. I open-sourced the model, which has now reached over 2,000 GitHub stores, reflecting strong community engagement and interest. This also enabled researchers to quickly apply Serfag to new datasets and models, leading to applications in expert domains such as biomedicine. Beyond the research community, Serfag has made a significant industry impact. It has been integrated into Llama Index LangChain, two of the most widely used frameworks for language model-based system, with tens of millions of monthly installations. Many media highlight Serfag as a key innovation to make industrial language models more reliable. This progress is exciting, but there is a caveat. To fully unlock the potentials of models like Serfag, we need a strong retrieval foundations. Before moving on, I want to briefly highlight my work on substantially improving retrieval foundations and retrieval models. While previous work often relies on small general domain data store like English Wikipedia, language models scale their pre-training data to trillion token level. Thus, scaling the data store for retrieval-augmented language models provides similar benefit. To answer this question, we developed MassiveDS, the largest open-source data store containing 1.4 trillion tokens powered by neural retrieval system. Building it requires overcoming major system-level challenges, including managing 22 terabyte storage and 15 terabyte CPU memory requirements. We address this by developing a scalable distributed retrieval system. Our findings show that scaling the data store significantly enhances retrieval-augmented language models, improving both upstream language modeling and downstream task performance for the first time. Moreover, better retrieval systems can amplify those gains. So how can we build a more effective retrieval system? One that generalizes well across tasks and identifies the most useful documents from massive data store. Previously, the community trained separate retrieval systems for each retrieval task. Instead, we introduced a new paradigm, retrieval with instructions. This approach enables retrieval systems to dynamically adapt their behavior based on users' instructions, making them more flexible and task-aware. We pioneered this method by training and releasing the first instruction-following retrieval system, which quickly set a new standard. Today, most of the state-of-the-art retrieval system on popular benchmarks, including NVIDIA's top-performing open models, follow exact framework introduced in this work. This approach has also been successfully extended to multimodal retrieval cases. Now, let me summarize part 2. I covered the key limitations in common retrieval-augmented generation pipeline, including the inflexible design and limitation of using off-the-shelf models. I redesigned retrieval system and language model to enable adaptive retrieval augmentation across diverse tasks at the inference time. I developed a scalable retrieval system and demonstrated the benefit of leveraging much larger data stores. Our work has set the foundation for new state-of-the-art models in this field and has been widely adopted in major libraries and industry applications. Building on those foundations, now I'd like to show how retrieval-augmented language models can drive real-world impact, particularly by assisting scientists across diverse disciplines. As scientists, we've all witnessed the rapid growth in the number of scientific publications. This plot shows the monthly paper submissions to arXiv from 1995 to January 2025. As you can see, the number of submissions has consistently increased over the past 30 years, and arXiv now hosts 2.6 million papers. It's worth noting that arXiv is just one of the many preprint servers. There are many others that host different collections of papers along with open access paper registries and licensed journals. This is exciting, but it also presents a significant challenge for many of us, staying up to date with the ever-expanding body of literature. The current language models truly help us to stay up to date with scientific literature. Remember the question I gave in introduction. As you can see, even state-of-the-art systems like GPT-4o frequently hallucinate, failing to generate accurate citations from their knowledge. Our analysis show that even in top-performing models, 78 to 92% of generated citations are entirely fabricated. Static language models also struggle to keep up with our rapidly evolving world, much like GPT-4o failing to recognize itself a year after release. This issue is even more serious in fast-moving fields like science. So how can we build an AI system that scientists can truly rely on? I argue that the answer lies in retrieval-augmented language models. To demonstrate this, I developed OpenScholar, a fully open retrieval-augmented language model that helps scientists synthesize scientific literature. I led a year-long collaboration with 25 researchers from 7 institutions across academia and industry. This large-scale effort brought together experts from AI, ML, HCI, physics, and biomedicine. In addition to the model development and benchmarking, we also released the first public demo of its kind so that scientists can interact with the system without the hassle of setting up everything by themselves. Now let's examine how OpenScholar answers the initial question regarding language models' ability to synthesize scientific literature. OpenScholar generates a response under 20 seconds, accompanied by extensive citations. Each citation comes with a short snippet, allowing experts to easily verify the information. Notably, OpenScholar can even cite itself. This stands in contrast to GPT-4o, which struggled to recognize its own existence. Now, let me show how we developed the OpenScholar system, building on the foundation laid in previous sections. There are 2 key challenges. First, how can we effectively evaluate systems in expert domains? While earlier sections show that retrieval-augmented language models have strong performance on existing dataset, those primarily cover general domains. This leaves a significant gap in resources needed to reliably evaluate progress in domains like science. Second, how can we enhance model performance in such resource-scarce setting? We often lack training data for language model or retriever, or even don't have a high-quality, up-to-date data store. Both are substantial challenges. For language models as scientific assistant, there has been some progress in automating literature review or idea generation. However, due to those challenges, prior work often relies on off-the-shelf proprietary language models and synthetic unrealistic operations, such as multiple choice question answering format. We first established a new benchmark, SCALA-Q events, a large-scale benchmark with a multi-dimensional evaluation framework to reliably evaluate models for development. SCALA-Q events include 7 high-quality datasets, categorized into 2. Single paper tasks where questions are answerable based on a single paper, and multi-paper tasks where questions require reasoning across multiple papers. For single paper tasks, we adapted existing datasets for retrieval-augmented scenario. However, we found that there's a major gap in resources for multi-paper synthesis. To address this, we recruited dozens of expert annotators, either Ph.D. holders or Ph.D. candidates, who created over 2,000 open-ended research questions and 200 expert-written answers. This dataset supports diverse output formats to accommodate different evaluation needs. Multiple choice and classification for simple, reliable evaluations, and long-form generation for more realistic scenarios. It also covers full field, computer science, biomedicine, neuroscience, and physics. Now, let me highlight 2 key subsets, SCALA-Q Multi and SCALA-Q CS. SCALA-Q Multi include questions from 3 scientific disciplines, computer science, biomedicine, and physics. Expert annotators crafted questions based on the latest scientific research. They then conducted literature review by themselves and composed detailed long-form answers accompanied by citations. Each annotation takes an average of 58 minutes, highlighting the time-demanding nature of this task even for domain experts. In SCALA-Q CS, annotators design rubrics with criteria for evaluating responses, assigning weights to each criterion. Some criteria are critical and must be included, while others are optional but enhance the quality of the answer. Using those rubric annotations, we introduce a new evaluation schema. For each rubric criterion, we use a language model to assess whether the answer meets the requirement. Here, the answer briefly mentions the key point, so the evaluator language model will say, this point is satisfied. The scores are then weighted based on the annotated importance score of each criterion. This approach enables a more reliable automatic evaluation compared to traditional string matching-based evaluation. Now, let me discuss how to develop systems that can perform this complex task. Built upon our foundations in part 2, we develop an efficient yet powerful pipeline with fully open components. A high-quality, large-scale data store is essential, as discussed in part 2. In collaboration with Semantic Scholar, we collected 45 million open access scientific papers up to October 2024. Building on the efficient pipeline from massive DS in part 2, we developed the OpenScholar data store, the largest and up-to-date data store of its kind. We update the index on a weekly basis in our public demo to maintain the relevance and freshness. This enables us to incorporate newly released papers easily, as shown in the demo, while OpenScholar can cite itself. Now our full-text search is available via the Semantic Scholar API. Next, we extended the self-style self-refinement approach to improve the integration of retrieval and generation. The language model first generates an initial response, which is then fed back into the models to generate natural language self-feedback. If needed, additional retrieval is also performed. After that, the language model finally defines its output by incorporating the initial response, feedback, and additional retrieval information, repeating this process as necessary. This iterative approach not only enhances the quality of generation at inference time, but also enables us to create high-quality synthetic training data. We use this data to train the open language model and retrieval system for this task. For more details, please refer to our paper. Now let me go over the result. Here we evaluated Llama C8b and GPT-4o without any retrieval, requiring them to generate the answer with a list of citations purely from their parameters. We found that both models achieve nearly zero citation accuracy, as most of the United citations are entirely fabricated. Standard bug baseline with our new OpenScholar data store demonstrates improvement in both accuracy and citation F1, highlighting the effectiveness of the retrieval-based approach. However, we found that, especially on top of open Llama C8B model, the citation accuracy is still relatively low. Lastly, the new OpenScholar training and inference pipeline, which indicated as pink bar, gives constant improvement on top of such standard bug approach, especially improving the citation accuracy on top of open models. We also compared OpenScholar 8B, a fully open system, with two proprietary production systems, Perplexity Pro and PaperQA2, which use much larger private language models and users needed to pay for. OpenScholar outperformed them by 5 to 10 points in terms of accuracy. We also conducted systematic evaluation across 3 scientific disciplines: computer science, biomedicine, and physics. Ph.D. level expert compared expert-written answers with model-generated ones, selecting their preferred responses. We evaluated 3 systems: GPT-4o, OpenScholar 8B, and OpenScholar with GPT-4o. The results show that OpenScholar GPT-4o generated answers were often judged less helpful than expert-written answers. In contrast, both OpenScholar 8B and OpenScholar with GPT-4o were preferred over expert-written answers, demonstrating their effectiveness. OpenScholar was the first open research synthesis tool before major companies started releasing their deep research features. It has been recognized in media and academic community as a new tool to advance language model for science. Our public demo attracted more than 10,000 users in first week, with over 30,000 practitioners and researchers now having tested it. We've received a lot of positive community feedback stating that OpenScholar is more reliable than existing systems like GPT-4o. What excited me most is that OpenScholar is being used beyond computer science community, impacting diverse field, as shown in this plot. In summary, this part covered our OpenScholar project, which built retrieval-augmented systems to help scientists synthesize scientific literature. We developed a new benchmark across 4 scientific disciplines with PhD level expert and created scientific papers to construct up-to-date largest data store. We trained language models and retrieval systems and released a public demo, now actively used by experts across different disciplines. This holistic approach, building retrieval-augmented language models for real-world needs, are also highly effective in other expert and underrepresented domains. I have demonstrated the effectiveness of retrieval-augmented language models for code generation and pioneered cross-lingual retrieval-augmented language model to improve information access across languages, especially under-resourced languages such as African languages. Let me quickly summarize today's talk. First, I discussed the key limitation of simply scaling language models via training data or model size, and demonstrate that retrieval-augmented language models can overcome those challenges, making them more reliable, adaptable, and efficient. Next, I outlined how we can establish new foundations by designing and training core components, which has now been integrated into major libraries and state-of-the-art models. Finally, I highlight the real-world impact, particularly in expert domains like scientific literature synthesis. Our OpenScholar system outperformed proprietary models and even expert humans, and now used by over 30,000 researchers. Now, let's discuss what comes next. My long-term research vision is to reimagine language models by transitioning to augmented language models, systems that focus on designing, training, and deploying language models in conjunction with complementary modules. What challenges remain in building such systems? First, this talk focused on retrieval-augmented language models with text-only data store. Those models are now widely used, and their applications are expanding to the scenario where data stores include heterogeneous knowledge, such as image, audio, video, domain-specific data like structured record, or DNA sequences even. How can we develop effective retrieval-augmented language models that excel in such complex scenarios? I have contributed to some of the earliest work in this area, focusing on multimodal retrieval and reasoning over diverse formats, such image, table, and knowledge graphs. However, previously we often relied on separate pipelines tailored to each modality or data type, which are then combined in a post-hoc manner. This fragmentation limits efficiency and integrations when we try to build general framework, going beyond simple tasks. Today, we are seeing the rise of multimodal language models that seamlessly process and generate diverse outputs beyond text, including our latest state-of-the-art multilingual multimodal language models. However, retrieval-augmented language models for multimodal input and output remains largely underexplored, especially beyond text and images. In my future work, I aim to advance retrieval and multimodal language models, enabling seamless processing across heterogeneous knowledge, especially for emerging and underrepresented modalities. This naturally extends to module orchestration, where multiple components and language models collaborate to optimize overall system performance. While retrieval remains a key, other modules also enhance predictions and efficiency. These include symbolic engine and reward models for refinement, external simulations or computing engines for heavy computations, and smaller special language models, or API, that boost domain-specific performance while cutting the cost. Building those systems beyond private language models and static APIs poses significant challenges across the entire language model development pipeline, from data collection, training, and inference. One of the biggest hurdles is a lack of large-scale data that naturally captures such complex interactions. Creating synthetic or real data and efficiently training models on it is crucial. In Certifag, we showed the power of synthetic data-driven training. The next step is to enhance data generation for more complex cases with many modules and enable dynamic training while keeping the cost manageable. Optimizing inference for the augmented language model is both a challenge and a huge opportunity. Recent advances like ChatGPT-o1, OpenAI's most advanced models, show how test time scaling boosts performance. Generating extra reasoning steps or multiple answers improves model accuracy. However, real-world use requires balancing performance and efficiency, considering factors like latency or resource usage. O1, for instance, can take minutes to hours for a complex task. I believe better orchestration strategies can maintain strong performance while making inference significantly faster and more efficient for real-world applications. Indeed, our work has shown that retrieval-augmented language model can significantly reduce training time computation. Moving forward, I aim to further improve data creation, learning, and inference by collaborating with experts in AI, ML, and related fields like system, bringing my insight as a language model expert. Finally, I aim to collaborate with experts to evaluate both the potential and risks of augmented language models in emerging field. Those models can drive advancement in complex areas like science and healthcare, but also poses risks, including safety and legal concerns, such as copyright issues. As seen with OpenScholar, ensuring real-world impact while mitigating risks requires expert-in-the-loop model evaluations and careful model development. Moving forward, I will continue exploring new applications of augmented language models, fostering cross-disciplinary collaborations to build responsible and impactful AI systems. Lastly, I'm grateful for the incredible collaborations with researchers from universities and industry that made this work possible. I would especially like to thank the amazing mentors who supported me throughout my PhD journey, especially my advisor, Hannah, whose incredible support and guidance helped me to grow from a naive undergrad student from Japan into an independent researcher. Thanks for listening to my talk, and now I'm happy to take any questions.
Any questions?